This brings us to the idea of ephemeral data structures. Normal data structures that we have seen so far are ephemeral, in a sense that the new updates destroy the old versions of the data structures. This is what we consider normal. In other words, imagine that you're doing an update in a binary search tree. You change some pointers, you rewrite some values, and you don't save the old structure of the tree. Contrast to this, a persistent data structure remembers the past, remembers the previous versions of the data structure. If you have worked with any kind of version control system, such as Subversion, JIT, or etc., Overleaf, I guess maybe even Dropbox, I'm not sure. You're familiar with this concept that you could have a file, for example, you could make some changes to the file, and then you realize that, oops, you've made a mistake. You could go back to the, let's say, to the version of the file that was there, 2 months ago, etc. In other words, some repositories can remember any old version of the file or system you're working with. And now we want to implement the same thing for data structures. Let me explain what this means. So implementing this idea comes in two flavors, a partial persistent and a full persistent. So one-line definition of partial persistent is that it allows queries in the previous versions, but only the most recent version can be updated. And a more rigorous definition is something like this. Imagine that you have a data structure that is being constantly changed. In other words, a sequence of updates constantly arrive at this data structure. You have the first update, the second update, the third update, etc. These updates could be deletions, insertions, or whatever operation that you can think of. A partial persistence allows you to add one more update at the end. So in other words, if I have 9 updates, I could add an update number 10 after them. But it allows me to query any prefix of the updates. In other words, I could query the data structure that was there after updates 1, 2, 3, and 4. I could also update after 1, 2, 3, 4, 5, 6, all the way up to 9, and so on. That is called a partial persistence. So you cannot change the past, but you can remember the past. You can query the past. Full persistence allows updates in the previous versions, and this leads to a version tree. Again, if you worked with, for example, JIT, you're very familiar with this concept of having a version tree. In other words, you have so this tree represents the different versions of this data structure. At any point in time, you could fork any version. So for example, you could add another update at this branch. So for example, update, 14. Okay. And you can also query any version, which means that you could pick any node in this tree, look at the path that connects this node to the root. That defines the data structure. So this defines the data structure after the update 1, 2, 4, 7, and 10. And then you can query that data structure. Obviously, full persistence is much more general than partial persistent, because any partially persistent data structure is full persistent. In other words, you get partial persistent if you don't have a tree. In other words, if you always fork the most recent version, which basically means that you only update the most recent version. So something that this doesn't capture that exists in JIT is that you can merge two branches, right? So this thing, this doesn't exist in this model or in this view. Okay, one of the most amazing theorems of data structure is the following theorem, that if we have any pointer-based data structure such that any cell or any memory location is only pointed to by a constant number of pointers, then you can make this fully persistent with essentially constant number of times time per update. And you can also make it partially persistent with constant multiplicative worst case space overhead. So for example, what is an example of a search structure with constant number of pointers to any node? A most famous example is a tree, right? So you have a tree, you have a root. Root has 2 children, let's say, and the children, every child can have a bunch of up to 2 children. You could even have multiple children, let's say. So in a tree, how many pointers point to every node? Well, it's at most 1. the root has 0 pointers to it. Every other node has exactly 1 pointer from the parent. So in a tree, this O of 1 is actually just 1. And what does it mean? What does it mean to be made partially consistent with O of 1 amortized update time? It means that if you want to change any this data structure, for example, change this, instead of this guy pointing there, points to some other node, the data structure can remember this at essentially constant extra space per update. So in other words, changing essentially doesn't cost you anything, or it's only cost constant time. In the next video, we're going to see how this can easily be combined with the sweep line approach to give a solution for point location data structure problem.